Hello everyone and welcome. If you're gearing up for big competitive exams like the TNPSC AE, SSC JE, or even GATE, then you have landed in exactly the right place. Today, we're going to absolutely master the Centroid. This is one of those topics that can be a guaranteed source of marks, but only if you know the smart way to solve it. So let's jump right in.
Okay, here's our game plan for this session. We're going to start with a super quick recap of the fundamentals. Then we'll dive deep into two very different ways to find the centroid. We'll start with the theoretical approach, so you understand the why behind everything. After that, we'll unleash method 2. This is the faster, smarter way that's built for your exams. And to wrap it all up, I've got a challenge for you to put your new skills to the test.
All right, first things first. Let's make sure our foundation is rock solid. We're just going to do a quick revision of the essential properties of the centroid. This will make sure we're all on the same page before we get into the heavy calculations.
So just remember, the centroid is simply the geometric center. You can think of it as the perfect balance point of an area, and it always lies on an axis of symmetry. So if you've got a shape like a rectangle or a circle with two axes of symmetry, well, the centroid is right there at the intersection. But the most important property for us today, a truly universal property, is the moment principle. The first moment of area about any axis that passes through the centroid is always 0. This is the secret key we're going to use to unlock everything.
Okay, let's get into our first method. I like to call this the theoretical way. This is our foundational method. Now, it might seem a little bit longer, and it is, but it is absolutely crucial for understanding why the formulas we're about to use actually work.
The entire heart of this method comes down to this single, powerful standard formula. The sum of the moments of all the little component areas about the centroidal axis has to equal 0. And remember, a moment is just a fancy word for the area multiplied by its perpendicular distance to the axis. So our whole strategy here is to assume a location for the centroid, and then use this universal property to prove that the moments on both sides of that line perfectly cancel each other out.
Let's see this in action with a simple rectangle. First, we're going to start by assuming the centroidal axis is at some unknown height, y bar, measured from the bottom. This is a value we've assumed just for this example. Now, this axis splits our rectangle into a top area, A1, and a bottom area, A2. So according to our core principle, their moments have to add up to 0. But notice the critical sign convention here. The distance for A1 is positive, but the distance for A2 is negative because it's below our assumed axis. After you work through the algebra, the calculation reveals that y bar equals d over 2. This is our calculated result, and it proves what we already knew intuitively. The centroid is right in the geometric center.
Okay, the rectangle was easy, right? But how does this theoretical method hold up when you're faced with a composite shape, the kind you're actually going to see in your exams? Let's take this method and apply it to a much more challenging I section.
All right, here's our problem. We've got an I section with these dimensions. Now remember, every single one of these numbers is assumed only for this example, just to illustrate the method. The total height is 700 millimeters, so the geometric middle is right at 350. Now pause for a second and just think, will the centroid, our balance point, y bar, be above or below that 350 millimeter mark? If you look closely, that top flange has a way bigger area, right? So your gut feeling should be that the centroid is going to get pulled upwards, somewhere above 350. Let's do the math and prove it. And this is where this method really shows its complexity. We again assume our centroidal axis is at some unknown distance y from the bottom. Then we have to split the section into 3 different areas, all relative to this unknown axis. Now just look at that centroidal distance column. Every single distance is now an algebraic expression with our unknown y. And notice the distance for the bottom area. It's negative y divided by 2. That negative sign is a critical detail, and believe me, it is a very frequent source of errors in exams. Setting up this full equation and solving for y involves some pretty tedious algebra, which can easily lead to mistakes when you're under pressure.
So, after grinding through all of that complicated algebra, this is the step-by-step calculated result that we finally arrive at, 440 millimeters from the bottom. And hey, just as we predicted, this value is well above the geometric mid-height of 350 millimeters. So, the method works, but wow, that was a lot of effort.
So we got the right answer, but that was a long, tough road to get there. And this brings us to method 2. This is the real payoff. This is the smart, efficient method that is going to save you precious minutes and help you avoid calculation errors in your exams like the SSC JE and GATE.
I mean, seriously, think about it for a second. Did that last method feel practical for an exam where every second counts? All those variables, the negative signs, the quadratic equations? There has to be a better way, doesn't there? Well, of course there is.
And here it is. Welcome to the reference axis method. The principle here is so much simpler. Instead of guessing where the centroidal axis is, we just choose a convenient reference axis, like the very bottom edge of the shape. The total moment of the entire area about this new axis is simply equal to the sum of the individual moments of its parts. And this gives us this beautiful, simple standard formula. By picking the bottommost line as our reference, all of our distances will be positive, and that eliminates the #1 biggest source of errors.
All right, let's put this new method to the test. We're going to solve the exact same I-section problem we just did, but this time we're using the reference axis method. Just watch how much faster and cleaner this is. Now, just look at the simplicity on this slide. It's night and day. We just divide the shape into two simple rectangles, the top flange and the web. We calculate the area and the centroidal distance for each one, both measured from our convenient bottom reference axis. The main point? No negative numbers, no complex variables, just straightforward multiplication. This is a much, much safer way to do things in an exam. Now, we just plug our totals into that simple formula, the sum of the moments, which is 44 million, divided by the total area, 100,000. And what's the result? Exactly 440 millimeters. This is our calculated result, and it brilliantly shows the power of picking the right method. It's not just faster, it also dramatically reduces your chance of making a silly mistake.
So let's just put these numbers right next to each other. The geometric middle of the shape, which was an assumed reference point, is at 350 millimeters. But the true balance point, our calculated centroid, is way up at 440 millimeters. That's a pretty significant shift upwards, isn't it? So, why does that happen? Let's pause and think about the actual physical meaning of the centroid again. What property of the shape's geometry caused this balance point to move up, away from the simple geometric center?
The answer is actually really simple. The area pulls the centroid. The centroid will always shift towards the part of the shape that has more area. In our I section, the top flange was way wider than the web, so it had more area weight. The crucial point is, you can think of it just like a seesaw. The heavier person makes the balance point shift. The larger top flange pulls that overall balance point up towards it. This is an amazing intuitive check you can use in your exam to quickly see if your answer even makes sense.
You've seen the hard way and you've seen the smart way. Now it is your turn to put this powerful method into practice. Let's really lock in your understanding with one final challenge problem.
Okay, here's your homework problem. For this L-shaped section, you need to find both X bar and Y bar. And of course, all the dimensions you see here are assumed only for this example problem. My strong recommendation is to use method 2. Set up your reference axes at the very bottom and the very left edges so you can keep all your values positive. Go ahead and pause the explainer right here. Give it a shot and see what you get.
All right, are you ready to check your work? These are the final calculated results you should have gotten. Y bar is 230 millimeters from the bottom, and X bar is 140 millimeters from the left. If you got these, that's fantastic. It means you have successfully applied the SMART method. Okay, let's wrap up with the most critical takeaways for your exam. First, always use method 2, the reference axis method. It's faster, it's easier, and it helps you avoid those killer sign errors. This is easily a 2 to 3 mark sure shot question. Second, always choose the bottommost and leftmost edges as your reference axes. That keeps all your distances positive. And be really careful about the most common mistake. Always measure the perpendicular distance from the centroid of each small shape all the way back to your chosen reference axes. And finally, why is this all so important? Because mastering the centroid is the essential first step to understanding the next critical topic, which is the moment of inertia and concepts like the neutral axis in beams.
Always remember, the only difference between being ordinary and being extraordinary is that little bit of extra practice. Keep solving these problems, stay consistent, and you will absolutely achieve your goal. Thank you for joining this deep dive. In our very next session, we are going to build directly on this knowledge as we tackle the moment of inertia. I'll see you then.